Cool. We're going to talk about knowledge graphs today with Neo4j. And in particular, we're going to look at a very, very simple machine learning approach for how we can create knowledge graphs. My name is Claire Sullivan. I'm a data science advocate at Neo4j. Here's a couple ways you can find me on the internet. And one of the things, the very last one there is on Twitter, my Twitter handle. If you don't get your question answered today, feel free, or if you have comments, feel free to reach out to me on Twitter. I check it quite regularly. So let's dive right in. Okay, all knowledge graphs. All knowledge, in fact, is controlled by Google. Okay, yeah, let's talk about, I'm going to put this link up a few times today. We're going to be working from some code that exists on my GitHub. I'm going to leave this up here for just a second here, but all of the code that you're going to see today is there. All of the slides, and I'll mention this many times, the slides will be there. So yes, you'll have access to the slides. The video for this workshop will also be posted, so you can access both. So if you have to pop in and out or whatever, cool. So let's get to the next slide. Okay, what are you going to need if you want to run today's code? You don't have to run it. You can just watch and learn what you want, or you can drive along with us. And today we're going to be using either Jupyter or Google Colab. I'm going to use Colab today. If you are going to use Jupyter, we're going to have some dependencies that you're going to need to install on your machine. I'll show you what those are in a minute. And then we're also going to be using Neo4j sandboxes. Now, sandboxes are free instances. Okay, so we're just going to spin them up and spin them down with reckless abandon. And hopefully you'll get a feel as we go along for how you can use Python to connect to those instances here. I'm going to throw a question out to you all, though, to put into chat. Let me ask you, when do you think the idea of a knowledge graph first came up? Okay, so throw your answer into chat. I'll give people a second here to answer that. I'll try to get to those here. So don't be shy. Just throw out your guesses in chat. We're going to have several of these things, several questions I'm going to ask you throughout the course of this workshop where you can throw your answers into chat. I see Houston and I see the UK. 2015, Kiran, I hope I'm pronouncing that correctly, says 2015. I've got Alexander saying the 70s, 25 years ago. The aughts. I'll tell you, one of you is pretty accurate. Okay, about 10 seconds. Jerome with the 2000s, Juan with the 90s. Okay, with Euler in the 1700s, love it. Okay, I'm going to tell you here that there's a couple correct answers here. I like the Euler in the 1700s because in reality, you can think of everything as a graph or as a knowledge graph, okay? And Euler had this idea of knowledge graphs dating way back. But a lot of times what people like to say, the answer is 1972. So who was it? Oh, Alexander said the 70s. So 1972, there was this work on how to build modular instruction systems. But then you could also say 1985. Oh, okay, Euler's the 1800s. Yeah, maybe I'm bad with history. But I also know that in 1985, semantic relationships in WordNet came along. So that's another correct answer there. And I'm going to ask you another question really quick. Can you give us some common examples of knowledge graphs? Where do you think we see knowledge graphs? So why don't you throw your answers into chat, some common knowledge graphs? Sad that I don't actually know when Euler was doing his thing, but it was a while ago. Okay, where can you find examples of knowledge graphs? Fraud detection. I would call that an example of a graph in general, but yes, if all graphs are knowledge graphs, absolutely. Recommendation systems, love it. Right column in Google search page, ontology, phenotype, voice assistants, yes, all of these are correct. Thank you for throwing those ideas out there. So we're actually going to work a little bit with some existing knowledge graphs out there, namely the Google Knowledge Graph. But we're gonna talk a bit today about how to create your own knowledge graph. So, machine learning. We're going to do some machine learning today, and while this is a fun one from XKCD, you just pour your data in and do some math and get some answers out. And if you don't like the answers, you just keep trying at it. And I don't want to say that's 100% accurate, but what I want you to take away from this is any graphs, any machine learning, garbage in, garbage out. If we don't have good data going in, we're not going to get good answers going out. So we're going to do our best to get as good of a data we can with as simple of a model as possible today. Okay. By the end of this workshop, you're going to be able to apply data science and machine learning to a knowledge graph. But in order for that to happen, we have to, I'm going to use these terms, I'm going to explain these terms a little bit down the road here. We have to vectorize our knowledge graph. That's the process of turning a graph into math. Okay, and that happens through graph embeddings. But of course, we have to have a knowledge graph to start with. Okay, so we're going to create a knowledge graph, but we have to first get some relevant text. And that's the process that we're going to go through today. Is we're going to start with raw text and we're going to extract information about it. And that's what we're going to use to create that knowledge graph. Now, the first two steps here, the first half is we're going to use natural language processing, which is a common machine learning approach for understanding text. Once we have that knowledge graph created through NLP, then we're going to use the graph data science learning or library and some basic machine learning to start understanding our graph a bit. Okay. Now, if you take away nothing else from this class, I would like you to remember these two things. First, there is no proverbial quote unquote silver bullet with natural language processing. NLP is hard. There's a reason when you go on to like job sites, you can find people who are specifically looking for NLP expertise. It is hard. Language is noisy, okay? It's very difficult to get, what I would call 100% solid signal out of noise. Secondly, the quality of what you put into a knowledge graph, or the quality of what you get out depends on the quality of what you put in. That's that garbage in, garbage out concept. Okay, so we're going to have our knowledge graphs that we're going to create, and they're going to be a bit noisy, I'll tell you that right now. But we're going to deal with it through a graph, and hopefully you can see that working with it with a graph is going to make it a little easier. All right, let's talk quickly about what a knowledge graph is. This is just a real simple one. It's a pretty common example. And what we've done is we've created a knowledge graph around the Mona Lisa. Okay, so the Mona Lisa is in the Louvre. We can see that it was painted by Da Vinci, but we also see some other bits here, like James. James likes the Mona Lisa, and James has visited the Louvre. James has lived in the Eiffel Tower? Probably not. Okay, so this is one of those cases where we can get some noise here just by doing, some natural language processing. Now, somebody had recommended that you could use, recommendation systems with knowledge graphs. Okay, that is true. So let's look at Lily, for instance. Lily, we can see, is interested in Da Vinci and is a friend of James. Now, we know that James likes the Mona Lisa, so we could maybe infer that Lily would like the Mona Lisa as well, and we could recommend that to her in a recommendation system. It turns out knowledge graphs and graphs in general are great at recommendation systems. A lot of places, they'll try to, create some recommender systems or recommendation systems based on clicks. Clicks can tell you a certain thing, sequences of clicks can tell you a certain thing, but what they ignore is the relationships between the nodes in our graphs. And the nodes here are the circles, they're the things we're talking about, and the relationships are the edges. Those are those verbs that connect one node from another. I'm going to use that terminology a lot today. All right, so when we talk about knowledge graphs, Google famously gave this quote, "Things, not strings." Okay, so we are looking at the relationship between things when we're talking about a knowledge graph. We know that they're useful for search. You know, we had people throw out Google as an answer of a knowledge graph, question answering. You could have asked on the previous slide, where is the Mona Lisa located? Recommendation engines we've already talked about. And these can be generated in a lot of different ways. And I'm going to show examples of all of these. Co-occurrence of words in text, resource description frameworks or RDFs, and then this idea of subject, verb, object. Okay, so we're going to be working with subject verb object triples or SVO triples today, but I'll show you some examples of these things. First, word co-occurrence. I'm sure we are all just ecstatic to see more data about COVID-19. And here is a whole bunch of peer-reviewed literature about COVID-19. And what we see, the size of the node is representing the number of times that that term appears in text. So we've got all of these peer-reviewed journal articles, and we want to see how often different terms occur with other terms. So for instance, you see viral pneumonia here, which is, you know, roughly slightly off 12 o'clock. Viral pneumonia is a big red node. And then if you go from that node roughly to the 8 o'clock position, you see coronavirus infection. And both of those are big because in the papers they're referred to a lot. And they're close together and they're linked with each other because they co-occur a lot. Same with pandemic down at roughly the 6 o'clock position. Now, if you were to go a little further out in this graph, let's look at the blue section, which is kind of in the lower left. We see the largest thing there is SARS. Now we know that there is a viral similarity between SARS and COVID. Okay, so we're not surprised to see that co-occurring with coronavirus infection. If we look at the top in the yellow, we see male, female, adolescent, young adult, fever. We're talking symptoms and we're talking people in that yellow group. So what this should give you an idea of is not only is word co-occurrence creating us a knowledge graph, but we can also determine clusters in that knowledge graph based on subject area, which is kind of cool. RDF triples. So RDF triples, that's the resource description framework, and this is a standard that was created by W3, which is the World Wide Web Consortium. And what they're looking at here is semantic triples. Okay. And so we can see like our central node here, people EM contact me. I've got a relationship that's given by a web address to a person, which is in my top right. I've got a person's name, the full name, Eric Miller, and you can see the web link for that relationship there. So this is an RDF triple. If you're interested, I'm not going to go too far down this path today, but there is a tool called Neo-Semantics, which will do RDF triples for you. I'm going to show you at the end of this course a place where you can find a whole bunch of links, including how to extract RDF triples from Wikidata. So it's just a thing that's out there I want you to be aware of. Today, though, because we're using natural language processing, I'm going to use subject-verb-object triples, SVO. So I'm going to have a node that is of label subject. Okay, so in the case of our graph to the bottom here, my subject might be Da Vinci. Okay, and Da Vinci has a relationship to the Mona Lisa, the object, through a verb called painted. Okay, so here we're going to get into some computational linguistics, and that's just a fancy way of saying that we're going to try using NLP to detect the subject of a sentence, the object of a sentence, and the verb that connects them. Now, sadly, I am not very fluent in other spoken and written languages like you all might be. We're going to do this strictly in English. There are ways that you can do this in other languages, but I'm not going to have time to get those today. So you might want to try this in your language of choice after the workshop. Okay, let's talk about what you need to know here for doing NLP on raw text to create this knowledge graph. The first step here is we're going to do named entity recognition, or NER. So the NER, named entity recognition, is going to look for those subjects and objects within our raw text. We are going to create the SVO triples. Sometimes you also hear this as SPO triples, subject, predicate, object. What you're going to see, though, is that verbs are very difficult to reliably detect via NLP. We're going to do our best, and I'm going to tell you right now, I'm just going to show you a pretty, basic, hacky way to do it. And then the other thing I want to tell you is that obtaining SVO triples is very topic area dependent. So I want you to take away something very important from that statement, which is that when you're doing NLP, it is crucial to have subject matter experts available to you, especially if you're talking about very complicated subjects like that coronavirus example. You want doctors and virologists and epidemiologists available to you to help curate what your NLP is doing for you. Having an SME is very important. Okay. Let's give an example here. This text is probably really small. I don't expect you to necessarily be able to read it, but what this is the summary section of the Wikipedia entry for Barack Obama. And the particular NLP software that I'm using, I'm going to use all open source software packages today. The one I'm going to use to do the NLP today is called Spacey. Now, Spacey is really good at going through sentences and whatnot and detecting the part of speech of that sentence. So, for instance, that purplish lavender color are all of the people that Spacey detected within this blob of text here. We can see organizations are in that cyan color. So I see Columbia University, the Harvard Law Review, things like this. There's one reddish bubble, the Affordable Care Act. Obviously, that's a law. And that's obviously something that Barack Obama was pretty close to. So this is going to be our starting point for the named entity recognition. Now, another way that we can look at this is kind of cool. I don't expect you to be able to read this. This is part of the first sentence, and this is really neat for those of you who are a little further down your NLP path. You can actually think of NLP as a graph. Okay, so I see words, which could be my nodes, and they have connections to other words. For example, the fifth one to the right is the word is. And you can see all of these relationships coming out of is. I'll talk to you about why that's true in a second here. But I have relationships going to the left. I have relationships going to the right. And that's true for all of the words here. So let's talk about what that actually means. Okay. Sorry, I'm going to grab a drink really quick. Okay, so here's the first sentence in that Wikipedia entry. Okay, Barack Hussein Obama II is an American politician and attorney who served as the 44th President of the United States from 2009 to 2017. Okay, what we do when we do NLP, and this is for you students out there or the people out there who are not data scientists but working with them, this is how this is going to work. This is how NLP works. We're going to take our text, and you see that I break this up into every word. And we're going to get the lemma of that text. And what the lemma is the bare bones starting construction. So for instance, you see the word is. Is a version of be. Okay, so be is what we're going to translate is into. If you look a little further down, I don't have it highlighted, but you see the word served, past tense. We convert that to serve as the lemma. We can get tags here for the parts or parts of speech. Parts of speech are things like propositions, nouns, adjectives. But the thing I want you to pay attention to is that next column, dep, which means dependency. And the thing we're going to look for is this thing called root. There will be one, generally speaking, one root of every sentence. That is the thing that we're going to base this on, and they're the verbs. They're the most important verbs within the sentence, which is or be is the root of the sentence. We always look for that root. Okay, and then the final column is stop, indicates whether that word is a stop word. Stop words are words that add no real meaning to our sentence, such as the word the. The word the appears many, many, many times in the English language, and we don't really care about it. So what we do is we just kind of throw those out. Punctuation, we're going to throw those out. Numbers, we're probably going to throw those out too. But just so you can kind of get a feel for how this all works. Now, I want to bring your attention to Barack Hussein Obama II. Okay, we can see that the second is being called the subject, the noun subject. Okay, not really true, but that's just what Spacey detected it as. Remember, text is noisy, but I have three compounds before and subject. So what we can do is we can group those together. So everything in that blue box, we're going to group together as being one named entity, which that's pretty cool. Okay, here's another one. We have an object. So I see that dependency is p-obj. That means object. And it also has a compound, so that would suggest that that blocked together set, United States, would be one named entity. Okay, cool. All right, let's talk a little bit more. Actually, let me ask you a question here really quick. Say you have this sentence and we have a subject and we have an object. What's a way that you could get the verb that connects those two? I have a few verbs here. I have served, I have is. Okay, so how could we connect Barack Hussein Obama to something like the United States? I also see president here. That's another object that I have here. So just throw in the chat, what are some ways that you think that we might be able to connect? How do we find that verb? What verb is associated with which object? So I'll take a second here, let you throw your ideas into chat. What do you think? Connecting subjects and objects. Sometimes my chat gets a little jumpy and I see no text coming in and then a whole bunch of things coming in. Okay, not sure I understand the question. Okay, so what I have here is I've got Barack Hussein Obama. I've got the word is, which is my first verb. And then I've got the word served, which is another verb. How do you suppose that we would go from Barack Hussein Obama to the United States? How do we determine which of those two verbs applies to United States? Serve. Barack, verb saved, yep. Okay, so I got Victor and Nathaniel. Yep. How are you going to mathematically figure out which verb appear after the subject? Okay, the word is does appear after the subject, but maybe Kiran, turn that one around. Shortest path, maybe. Shortest path from word to word. I like that answer. That's cool. I hadn't thought about that one. You have to try that. Okay, the distance between words, that's another way you could do it, yeah. We've got a pretty big distance here between Barack Hussein Obama and the United States. So if you were to take one and Kiran and kind of combine them, and that's how I did it in the code that we're going to see today. So these are great answers. I love them. And so what I did in this code, there's a whole ton of different ways that you could do it. I chose the verb that was closest in space to the object. So serve is closer to United States than be. Okay, hacky, admittedly. If you were to use some more sophisticated machine learning tools such as transform models like BERT, you could probably get this a little more accurately. It's a little harder to use these transformer models, so I'm just going easy. Can you add weights to the words? Ooh, that's a good question. Could I add weights to the words? Let me think about that one, Nathaniel. I'm going to get back to you after I think about that a bit, but I love that question. Okay, so I'm just going to choose the closest verb to the object, and that's what we're going to do today. All right, let's talk a bit about the tools. Like I said, we're going to use Spacey. We're also going to use Wikipedia to go grab the text. That's how we're going to grab raw text. You could have tons of documents of your own that you're scanning in or whatever. But just for the sake of today, I'm going to use Wikipedia. We're also going to query the Google Knowledge Graph. Now, I'm not going to actually create a knowledge graph with it because I want you to see how to do that in Neo4j. But I'll show you what we're going to do with that in a second. Next, we're going to use PyWikibot. I'm actually going to show you two different ways to create knowledge graphs. Wikidata is another way that we're going to do it. I'll show you that in the second method that we do. And then, of course, we're going to use Neo4j and a few libraries. We're going to use APOC, the Awesome Procedures on Cypher. In case you haven't noticed, we kind of like our matrix references around here. One thing I want to tell you about APOC is that if you can't figure out how to do your thing in Cypher, obviously we're going to be using the Cypher query language, which is the query language of Neo4j. If you cannot figure it out on Cypher, chances are there is a way to do it in APOC. So if you're stuck, go check APOC, and you probably will find what you're looking for. And then the other one that we're going to use today is the Graph Data Science Library, or GDS. So GDS opens up a whole new world of our ability to do things beyond just analytics. We can do graph analytics. GDS lets us, as data scientists, do a lot more. Okay, I remind you again of the GitHub repository that we're going to be using today. Again, it's optional for you to code along with us, but if you want to, here's where you're going to need to go. Okay, I also, while I'm doing the reminders, I will remind you that the slides are in the repository, and we also will have links to the video of today that'll be available to you, and I will also be sure to put those in the repository. Okay, we're going to do two methods today. I mentioned that we were going to use Google Knowledge Graph and we're going to use Wikidata. We're going to start with method one, which I call the NLP Only Approach. Okay, let me tell you what that is. Okay, the NLP Only Approach means we start with text and we clean it. For those of you who are new to data science, I like to say that at least 80% of data science is data cleaning, like data janitor. Okay, we spend a lot of time cleaning things. We're going to then, from our cleaned text, get our named entities, and then we're going to get the subject, verb, object triples for both of those, or for all of those. And then we're going to assemble our graph. Now we could also, if we wanted to get sophisticated here, we could get the adjectives for each of those subjects and objects. I'm not going to do that today. I'll leave that as an exercise to the attendees. There are some significant advantages to this method one approach. First off, you have limitless verbs. Assuming you can detect them, you can put them in the graph. The next approach that I'm going to show you, not entirely true, but remember, verbs are tricky to get. So, it's kind of a double-edged sword there. One drawback to this, as we are going to see a lot, is entity disambiguation, when I have two nodes that are actually the same thing, but they were detected as separate things. So I'll show you examples of that. Okay. Once we have our graph, we're going to do some machine learning on it. And I want to mention just briefly some different ML approaches that we could do. For instance, one of the common ML algorithms out there is called word tovec. Now, when we have things that are not numbers, like a lot of times what we do when we do machine learning is we have a whole bunch of numbers in the form of a vector, and each of those might correspond to different columns within your data table or whatever. Everything that we do in machine learning is about have a vector, run some math on it, get an output. That's all of machine learning. Thank you for attending my TED Talk. But really, words obviously are not numbers. We have to turn them into numbers, and that's what word tovec does. Word tovec uses this skipgram approach. There's a link down there at the bottom if you really want to see the math. Also, go check out Tomasz Britannic, who's in chat right now. He wrote a really great blog post on how this works, and there are analogies to graphs that we'll be talking about in a bit. But basically what you start with is this document gave a research talk in Boston, and word tovec is going through and it's finding the similarities between each of these words. Okay, so we can see that Boston and Seattle, if we were to plot these 2 points, these 2 words, which is basically what we're doing is we're taking those word vectors and saying how close are those 2 vectors. Okay, so Boston is pretty close to Seattle, makes sense. Science is pretty close to research, but talk is not close to Boston. Those words are not very similar. So when we convert things to vectors, we can do word similarity. We're going to do sentence similarity, but it's going to work the same way. Okay, let's get a little bit more in detail about this workflow. We're going to get our Wikipedia entry for our starting search term, and we're going to do natural language processing on it to get all of our SVO triples. We're also going to add some properties to our node labels. So like, for instance, we know Barack Hussein Obama is a person. You'll see Mitch McConnell in that text. He's a person. We see places in there. So we're going to create node labels for all of those properties. Then we're dedupe, clean, dedupe, clean, dedupe, clean. We're going to go through that a lot. Like I said, data science, data janitor. And then once we have that all into the graph, we create what we called as an in-memory graph, or a graph projection. This is the backbone of everything that happens within the GDS library, Graph Data Science Library. Okay, then from there we create graph embeddings, just like word embeddings, but we're going to turn our graph into vectors of numbers, and I'll show you how in a bit. And then using those vectors, we do some machine learning. All right. The actual NLP part is pretty lengthy. We remove control characters and regex. We create a spacey doc. If you don't know how to create these spacey docs, that's fine. I'm going to show you how to do it. We find that closest verb to each object. We remove stop words and punctuations. We assemble tuples of SVOs. We remove duplicates, remove dates, all this stuff. Okay. Let's talk about a little bit how we're going to take our nodes, our subjects and objects, and add some data to them. Just having a, something that is called United States. Okay, that's an object. I want something more than just object. I want to be able to say place. I want to be able to say thing, law, stuff like person, stuff like that. So we're not going to do this today, but I'm going to show you all the code about how to do this with the Google Knowledge Graph. First, you have to create yourself an API, and that link on how to do it is right there. You drop down to that credentials page. It'll give you an API. Once you have the API, you throw it into your Python code. I show you how to do that in the code, and we're good to go. So when you see it in the repository, you'll know what it is. We get a lot of information back for a search term. And in particular, here I did a search for Taylor Swift. Okay, so that's my search term, Taylor Swift. Now, apologies to people out there who actually know a lot about Taylor Swift. I don't, but that's fine. So I can see here that Google identified Taylor Swift as being a thing and a person. Those are the things that are going to become our node labels within our graph. Okay, after I know that, I have this description here. Okay, it's usually, and they don't all have this. They don't even all have the types like thing and person, but we're going to use them when we have them. So here's this, roughly a few sentence description that you sometimes will see. I see Taylor Swift is a songwriter, singer-songwriter. I can see where she was raised, she moved to, all of these things. Now we're going to grab that stuff and we're going to throw it in the graph. We're actually going to vectorize that text. I run word tovec on all of that and come up with a vector that vectorizes all of those sentences. Okay, and then just for fun, if you wanted to enhance your knowledge graph even more, you could put the URL where you got that information, and we'll do that too. We're not going to use too much of that. I just wanted to show you how to do it. Okay, when we do that, here's going to be our graph model. I have a subject, and my subject is going to have the property of name. Okay, and then they're connected via a verb to an object. And the objects we get to have a little more detail on. It's the objects that I'm going to run through the Google Knowledge Graph. So I have name, I have node labels, of which there might be several, there might be none. We don't know. We're going to grab them if we got them. Description, that was that sentence thing, and then I have the URL. And then what I'm also going to add in is the word vector. And the word vector is vectorizing that description using spacing. Okay? When we do that, we're going to get a graph that looks roughly like this. Okay? So, let's get started right now with this. I'm going to quit out of my slides for a minute, and we're going to create a sandbox instance to get us started. So we're going to go to sandbox.neo4j.com. Okay, and this is what it's going to look like. It's going to ask us for a login. I'm going to just log in with Google. Do it however you feel like. Okay, and here we go. Here is our sandbox. Okay, we have all kinds of pre-built sandboxes here, but we're going to go, you see I have a row here that's called featured data set. I'm going to go to your own data, and there's this thing called blank sandbox. So we're going to click on that, and then we click on the lower left, create. Okay, and it's going to spin up a sandbox. It takes a minute. I'm going to give you just a couple seconds here to get your sandbox up and running. So if you're wanting to code along, create your sandbox. If not, just sit back and have some fun. I'll give you 1 minute for this one. Can we use an aura instance is one of the questions. I am going to recommend against, and the reason being is that in the free aura instances, the graph data science library is not in there, and we're going to be using it a fair bit. So I do recommend, if you ever want to use GDS, you use Sandbox instead. Thanks for the question, Alexander. All right, now what we're going to do here is we're going to open the Neo4j browser. Okay, and to do that, I just click this open button right here. If it doesn't load up for you right away, you might get like a 404 timeout error or something, and just give it a minute and reload here. Yeah, see right here, I should be getting like a little scroller bar. So just close this window and click open again. Bad gateway. Yeah, okay. Let's try it again. Okay, we're going to come back to that in a second here. While we're waiting, what I want to do is I want to take you into the repository and kind of walk you through that. The link for the repository is in the chat right now. You can see it there. So let's just walk through this a little bit. First off, you do not have to use a Sandbox instance to do this. You could use Docker. I have a Docker container ready for you here, but I want to I want to use Sandbox and Colab just for simplicity here. But if you want, there's a Docker Compose file here that I've written for you with your Docker file. Let me show you quickly the requirements.txt file. These are the packages that you're going to need if you're running this locally. I want to call out two different packages here. First is Neo4j. This is the official Python driver for Neo4j. We also have this package here called Py2Neo. This is a community written open source package. I'm actually going to show you how to use both today. They both have pluses and minuses to them. But let's just, so if you want to run this on your own machine, cool. And then I also have PyWikibot and Wikipedia here. And Wikipedia obviously allows us to scrape Wikipedia, and then PyWikibot, what that allows us to do is that's the bot that will go scrape wiki data. So those things, if you want to scrape them, that's what you will need, but you don't have to. I actually have the JSON files for the graph that we're going to be using. This is, okay, we're not going to be able. Yeah, it's a big file here. I show you in the notebooks what it actually looks like. But so if you don't want to do the scraping yourself, you can find the raw data there. Okay, let's see if it's going to cooperate now. Yes, okay, so you can see this little status bar. That's what you want to see to know that your browser is ready. Okay, so it'll take it a second to fire this whole thing up. Okay. While it does, I want to go back to the repository, and I'm going to show you a few things. All of the Cypher queries we're going to run today are within the cleverly named Cypher queries directly in the repository. So let's click into there. So I have starting queries, method 1 queries, and method 2 queries. Now I'm going to be asking you some quiz questions today, and after the workshop I will be creating another file here called answer queries. Okay, that's not going to be here yet because I don't want any cheating. Okay, but what I want you to do is I want you to go into this starting queries file here. Here's just a few helpful queries for how you can look at all your nodes, how you can delete your graph and start over. But I want you to take line 22 here. We're just going to copy that. This is how we're going to actually import our SVO graph. What I've done is I've done all the NLP already for this graph, and I'm going to walk you through how I did it. But we're going to just populate our graph here just really fast. This is going to take a minute. Let me blow this up a bit. Okay, so I'm just going to copy that query right in here. Okay, and we're just going to let that run. Now, while I let that run, I'm going to show you here how it is that we created this. Okay, so I have some additional slides in here that are HTML. So what you'll see in here is you'll see the PDF slides that I'm using. So this is in the repository slides subdirectory. Okay, and what we're going to do is I'm going to just open the ZeroLevel slide here. Okay, and this is going to describe how we do our NLP. So we're going to get started with method one. We're going to start by just importing a whole bunch of packages. We're going to do this in Colab here in a minute, some of it. I'm not going to run through all of the notebooks here. I'm going to run through kind of the pertinent ones, but you'll be able to step through all of the nitty-gritty details if you want to. So here, I told you that we were going to be using an API key for Google, and that's where it is. I'll talk about what this loading is here when we actually get to the notebooks. But basically what we're doing here is we're creating our Spacey pipeline that will automatically do all the named entity recognition for us. Okay, and this stuff, by the way, let me tell you where this is occurring. Okay, if you go into the repository and notebooks, this is occurring in notebooks 0 and 1. Okay, so like if I just look at these notebooks, and we're going to pray that GitHub cooperates here, this is what we could run in Colab if we wanted to do this from scratch. Okay, and I walk you through all of this. This is just the same stuff I was showing you before. Okay, I'm querying Google. I've got helper functions for text cleaning. Okay, that's what's in these slides here. So you can run this all on your own after the workshop. Okay, we queried the Google Knowledge Graph. Now, I remember I mentioned that you need a key for that. When you get that key, you can do up to 100,000 reads per day, which is cool, and that's just the free version. So, you know, I have functions here for how to do that. I have those helper functions for text cleaning. Okay, let's get started. So, this is the query that we do for getting the text on Barack Obama is our search term. You can put whatever search term in here you want. I will tell you that sometimes Wikipedia has some good text available. Sometimes it's rather limited. Your mileage might vary, but you can see the text. Okay, and so then I've got a whole bunch of helper functions, and what these do is they go get the object properties. So those are things like those descriptions and URLs and the labels for each object, and I just keep adding them to the graph. Okay, so if you run this step by step using functions in there, we're not going to do this today just because it's going to take a lot of time and we have limited time today. But I have this thing called create SVO triples, which does all of this for us. And we wind up, this is just the first 3 entities in the list of SVO triples. Okay, so you can see here that what Spacey detected was the phonetic spelling of Obama, which is interesting. We got a verb here, be. Okay, and an American politician. Cool. The second one, Obama be the 44th president. But then I get this other one, Obama be United States. Okay, probably not. Again, text is noisy. I'm going to go, I've got these functions to get the object properties, and I wind up with this list here that looks kind of like this. So this was actually our very starting term here. You can see in some places I have these things, these lists here. This is a node label, so Barack Obama is a thing, probably not. I mean, I guess depending on how you define it. Barack Obama be United States? No, but here is that description. And that description is what we're going to create our word vectors out of. And I can see now I have labels associated with that subject or that object, the object being United States, which I can see has these 4 labels put to it. Now, you know, Neo4j doesn't care. You can have as many node labels as you want for a node. Cool. Okay. Oopsie. Okay, let's see, where are we at? Okay, so we've got these tuples, and we're going to upload them into our graph. I wind up getting 681 nodes and 531 relationships. That's all good. The problem is when you do this, you're actually going to be missing something here. I'll show you what that is in a minute. we're going to walk through doing a lot of analysis on this graph, but we're not going to actually create the graph. We've actually already done that here. Okay, what we will be using this here, this is using Python Neo to create a connection between Python and Neo4j. And the one that I've highlighted here is if you're doing this through Docker, you just have this this link that's called Neo4j. When we do this through our sandbox instance rather than Docker, we're going to have an IP address. We're always going to go through port 7687, and we've got a password here. I'll show you how to get all of that stuff. But this is just how to set the connection up to Neo4j. Okay. We can do some entity disambiguation. I'm going to go through all of this in a bit. Okay, yeah, we'll go through this in a minute here. Now, what you will find out if you were to run Notebook 0 is that Michelle Obama does not appear in this graph, okay? And the way I know that, this Cypher query will, can show us that. So I see that the name of this node, there's no node that contains the name Michelle. This is where your subject matter expert is coming in. Okay, that SME can say, oh, wait a second, there needs to be this person who isn't in there. Okay, so now we know that we actually are going to need to do a little bit more work on our graph to bring in some more information. So that work is actually done in, come back here, into our slides. I'm now moving on to slides 01. Okay, I'm just going to cut to the chase here. We run all the same stuff, but what I do is I'm actually going to ask that we, this is all the same stuff as before, but in this case, I've already run my Barack Obama graph, but now I'm going to run a Michelle Obama graph separately and add it all into the graph. Okay, so that's how we get around that. Your subject matter expert should tell you what you're missing. Okay, so I wind up with 863 nodes and 654 relationships. Now, I will tell you that this will vary a little bit depending on, because Wikipedia is a living document. So that text might change a little bit from when I did those slides. When I made these slides, that's okay. It's all good. What I see here is that I have 862 nodes and 823 relationships. Now, just notice this error here that it's been terminated. It's terminated for a timeout problem. Because I know that's how many nodes and relationships are here, that's fine. We're not going to worry about that. Okay, so as long as you see these numbers here, you're good to go. Okay, so let me just make sure there's no other slides I want to cover here. We've added our nodes using the function called add nodes. We've added our edges using this thing called add edges, another word for relationships. It's all good. Okay, so we now have a graph. We have a populated graph. How do I know we have a graph? Well, I'm going to go back into the starting queries thing, and I am going to run line 8, which says match N. Actually, let me just go into it here so you can see it. Okay, Cypher queries. I'm going to go starting queries. And here, view all nodes is in line 8. So we're going to match N, return N. Now, if you're new to Cypher, what I want to tell you is that Cypher is a lot like ASCII art. Like if you use SQL a lot, this would be like select star. Okay, but when we use the round parentheses to us indicate node. Squares will indicate a relationship, but round indicates node. Okay, so we're going to match all nodes. This is like select star for our SQL friends in the house. Okay, we're just going to run that. Okay, and what that's going to give us is this big old graph. Okay, I can see that my phonetic spelling of Obama is at the center. I'm going to zoom out a touch. Okay, so I've got a graph here, and that's cool, but you see all of my nodes are of type node. Okay, so we're gonna want to fix that. So let's let's close out of here. One thing I want to tell you about browser is that it can get a little memory intensive. So if your queries start getting a little slow, just refresh the browser. But these visualizations are the things that take up the most memory. So I always like to close those when I'm not using them, just so I'm not dealing with any memory problems. Okay, so we've looked at our graph. Seems legit. Let's go back into the repository now. Okay, and I'm going to go to method 1 queries. Okay, we've looked at our complete graph, but now I'm gonna I'm gonna update my node labels based on that list that I created. Remember when we said Taylor Swift was a thing and a person? So I've given you the query here how to do that. Okay, and we're using APOC to do it. Remember I said APOC, if you don't know how to do it in Cypher, probably exists in APOC. Okay, so let's run this. We're running lines 12 through 15. Okay, so let's just copy and paste it in here. And I can hit the run button here, or I can do Control Enter. It's Control Enter in browser, it's Shift Enter in Jupyter Notebooks. Yeah, just gotta go with it. Okay. So now, let's see, I have all kinds of different node labels here. I've got the subject, who was Barack Obama. I've got orange things, which are nodes because they didn't have any labels associated with them in Google Knowledge Graph. Administrative areas are in pink. I've got organizations in blue, like Columbia University, but you can see it gets some stuff wrong. Okay, civil rights attorney here is not an organization. Again, this is noisy. NLP is noisy. Okay, cool. Let's go back to our query. Now, you remember I said that one of the problems that we're going to have is deduping. There were a lot of deduping steps that I just kind of talked right over when we were going through those notebooks here. Okay, let's find out how many nodes contain the name Obama. So for those of you new to Cypher, I've got round parentheses, node. It turns out that every node in this graph, it has at least the label node, if not anything else. I'm going to give that the variable here called n. And n has a property called name. And I want to say name contains Obama. And I'm going to return all of those distinct Obamas. Let's do that. Okay, give that a run. Okay, bummer. I've got Obama terms, Barack Obama, Obamacare, President Barack Obama, Michelle LaVaughn, Robinson Obama. Okay, not happy about that. Okay, so we got to figure out like Barack Obama and President Barack Obama and Barack Hussein Obama II. Those are all the same person. That is not fun. Okay. So we're going to have to deal with that. We're also going to have to deal with duplicates. But let's do a problem here. Where was Barack Obama born? Okay. So I want you to think about that. I'm going to tell you, think about this is a hint. Think about what the lemma of born is. B-O-R-N. What might the lemma of born be? There's actually a few ways to solve this one. And like I mentioned before, I have a file called answer queries. Okay, and that answer queries file will be uploaded to the repository afterwards. So take a second, think about how we might do that. If you have any suggestions or any code, please feel free to throw them into the chat. If you have any questions, also put them in there. For those of you who are comfortable with Cypher, I'm going to give you a suggestion. It might not be the best one, but maybe look at places that are within a certain number of hops from Barack Obama. Okay, in the interest of time, let me show you that number of hops one. And I think the SQL folk in the room are going to like this. Here's what I'm going to do. I'm going to match a node with the name of Obama, the phonetic spelling. Now, remember I said n.name before. This is just a different way of specifying that I want this property. So it kind of looks like a dictionary. Then I've got some ASCII art here. So remember I said that square brackets indicated relationships. You're going to see this a few times today, so don't worry if this is kind of new here. Okay, Dominique says born is a verb. We will find as the name of relation. Well, is born the lemma is the question. Okay, that's your hint, is born the lemma. Okay. Let me get back to this query here. When I use this asterisk here and then two integers, what I am telling Cypher is I want a number of hops. So I want anywhere between 1 and 5 hops of some node. Okay, now you notice the arrow here. This is my ASCII art. So I'm connecting this node here to my node called P. It's a directional connection. And the square brackets indicate my relationships, meaning 1 to 5 relationships away. Now think about how, this is like 6 degrees of Kevin Bacon here. Okay, how many degrees separated is node P? Now I said node P had to have one of these labels, country, administrative area, continent, place. Okay, but think about how that would be to write 6 degrees of Kevin Bacon within SQL. Okay, not fun is the correct answer. And so when we're talking about Cypher, it's just one line. But with SQL, it would be many, many, many joins. Here's a hint for you data scientists out there. How do you know if your problem is a graph problem? This is one of the most common questions I get asked. The answer is if you're trying to do the same thing in SQL and you have more than a couple joins, you really should start thinking about it as being a graph. Okay, because all of a sudden my multiple joins, and joins are slow. We know joins are slow. Look at how quick that was to write it in Cypher, and let's give that a run. Okay, and what I see here, I see a whole bunch of different places. I see, let's see, I see Russia, Libya, Illinois, United States. Okay, there's a whole bunch of places that I'm not real happy about in here. I do see Honolulu. Now, here is the hint. Right here, bear, B-E-A-R, bear is the lemma of born, okay? Bear is the lemma of born. We also might consider B, okay, but bear is the lemma of born. So using that, I'm going to rewrite my query now. And again, this is all going to be in the repository later today. Okay. So now here's what I'm doing is instead of saying 1 to 5 hops, I've replaced my relationship type. And I'm going to say my relationship is either B or bear. Let's see what we get. Oh, cool. Okay, I see Obama, bear, was born in Honolulu. I see Obama, B, United States. Okay, that's kind of accurate. I also see Obama, B, African-American president. That's coming up as a museum. So probably he wasn't born in a museum. That would be interesting. Okay, so cool. I have kind of a solution to that problem. Neat. All right, let's go back into the repository. I have another question here. I'm actually going to just work through, in the interest of time, I'm going to work through how many duplicates are there in this graph. Okay, and we're going to do this in Cypher. Again, this is going to be in the solutions file. How many duplicates are there? Let me explain this query. So I have my nodes. I'm going to match my node, and I'm going to get my names and my labels. Okay, and I'm going to collect. Collect means turn my response into a list. Okay, that's all that says. So I'm going to create a list of all of these nodes. I'm going to call that list nodes. And then what I'm going to do here is I'm going to say the size of nodes. In Python, we'd say like len, L-E-N, of a list. Okay, but if I have a length of greater than 1, that means I have a lot of nodes with this label. Okay, and I am going to return those nodes as lists, and I'm going to return the size of them. Okay, so this is again, let's see what we get here when we run this. Okay, I have a whole bunch of Barack Hussein Obama II's. In fact, I have 20 of them. Not cool. Okay, so we do have a duplication problem. We need to dedupe some more. Okay, now if I go back into my Cypher queries, oh, wait a second. That's not what I wanted to do. I am going to show you, that was how we find the number of duplicates. We're going to get rid of them now. So dropping duplicates. Okay, let's drop these guys here. I'll explain this query. Again, you remember we collected our nodes. We created a list, and we figured out which ones had a list greater than 1. And then for each of those, this is for each element in nodes, I'm going to detach and delete that element. What that says is just get rid of it. Get rid of my relationships with that element and get rid of the nodes with that element. So let's give that a run. This is for when it's greater than 1. Okay, so you see I had 205 nodes that were duplicates. Gah, not cool. Okay, now what are we going to do next? Let's come down here. Okay, you remember, let me just show you what one of the nodes looks like. So I'm going to match some node, and I'm going to return some node, and I'm going to limit it to 1. So this is like, SQL is like select star limit 1. Okay, so here I get my first node here. Now I see this as a graph. Let's look at it as a table. Okay, so I've just clicked this table button on the left here. I have labels, I have node and subject. I have properties, such as a node label of subject. Description didn't exist in Google Knowledge Graph, but here, remember I created word vectors with spacey? I just took a description and I turned it into a 300 vector, or in this case, it's a 300 dimensional word vector. Okay, now I could look at that in Python, but it turns out I can also look at that using Cypher. So like we could do cosine similarity in Python. I could also do that in Cypher. So let's do that. We're going to get, I'm going to have one node that's called N1 with the name Barack Obama, and I'm going to get the second node, N2, with the name of Mitch McConnell. Okay, so how similar are these two individuals? So I ran cosine similarity, and I thought that there is a 90% similarity. It's probably not based on their politics. It's probably based on the fact that they're politicians, they went to law school. I think they even went to the same law school of Harvard. So there's a lot of similarity, even though they're in two different parties. Okay, so cosine similarity on vectors, still possible. Now, you might consider Levenshtein difference to look at two nodes that might be the same. Okay, so we could say Barack Obama and just Obama, and what Levenshtein distance does is it says how many characters do I have to tweak before I come up with the same string. Okay, that's all Levenshtein distance is, and it's built into APOC, which is cool. From Barack Obama, what I can see is like to Obamacare, I have to change things 8 characters. Michelle Obama, I have to change things 24 times. You know, if you were to get some good similarity here, this could be a way of saying, you know, of deduplicating your graph, just another possibility there. Okay. Okay, cool. So we're We're going to now do some actual data science on this. You're probably thinking, oh, it's about time. So what I'm going to do is I am going to open slides, and I'm going to open slides 2 here. Okay, data science. Okay, so we've already populated our database. We've established our connection to it. In Python, I am going to show you how to do this. Okay, here's where we're going to get into Colab. Okay, actually, I'm going to come over here. Okay, so this is kind of a fun way to use Colab. I'm going to go more Google Collaboratory. Okay, so here I'm in my Google account. I'm going to say Google Collaboratory. Okay, and in just a second here, I get a notebook. We are going to go open notebook. Okay, and here I'm going to select GitHub. Let me zoom out just a touch. Okay, I'm going to click GitHub here. Now we're going to enter the GitHub URL. Okay, so let's just come back up here. We're going to go to the actual root so I can copy this in, just because I know that I would type this wrong. Okay, so I've copied my repo address in here. Okay, and I am just going to hit enter. Okay, and look at that. It comes up with all the notebooks in my repository. We're actually going to go to notebook number 2. Okay, and I'm going to open a new window just so I don't have to repeat this process for every notebook that we're going to run. Okay, now so I'm going to show you how to actually run this code. For notebook number 2, we're going to use Python Neo. Okay, it wasn't authored by me, run anyway. So what I'm doing is I'm just pip installing the package. Okay, so once it's done here, cool. Okay, I'm going to bring in just my typical machine learning data science packages. Okay, nice. Okay, now here's something I want you to know. We're going to do this a few times today. Okay, we need to use Python to connect to our sandbox instance. Okay, and in order to do that, I need the URI of my instance and I need the password. Let me show you how to get that. We're going to come back to just our normal sandbox launcher. Okay, and I'm going to click this down arrow. And you see it opened up a bunch of stuff, including connection details. Okay, connection details are where we get the Bolt URL and where we get our password. Our username is always Neo4j. So I'm going to just copy that Bolt URL, and I'm going to go back into my notebook and I'm going to paste that in here. Okay. Now I'm going to go get the password the same way. Passwords are always like these 3 words separated by a dash thing. So I'm going to copy that and I'm going to paste it in here. Okay, and I'm just going to hit Shift Enter, and I got no error, which means that we connected from Python to the sandbox. So cool. Okay, now we can do some entity disambiguation here. What I'm going to do is I'm going to match all of my nodes that are President Barack Obama, and we'll just return the name. And what we're going to do here is just create a list. Okay, so President Barack Obama was related through some relationship, I didn't specify what it is, to some other node. Okay, and the only node that I got back was Affordable Care Act. Okay, now let's do this also for the phonetic spelling of Obama. Okay, so let's give that a run, same thing. Okay, I got 115 nodes back that were related to Barack Obama, or this phonetic spelling of Obama. Okay, I'm going to turn those into sets and just look at the number of overlapping elements in each of these sets. Okay, it's the nice thing about sets. So if I compared the first one, which only has 1 node, to the second one, which has 15 nodes, I see that there's 100% overlap because that first node appeared somewhere in the 115. Now, if I flipped that, I would get the answer 1 divided by 115. So it wouldn't be good overlap. So maybe that's not the best way to disambiguate. It's going to depend on your graph. Okay, so let's do some graph machine learning. Whew. Okay, what we're going to do here is we're going to do a classification problem. We're going to try and predict if something is a person. It's not binary classification, it's multi-classification. What am I thinking? Okay, person, place, thing, or unknown. Okay, cool. We're going to create some labels around this though, because it's going to be a little, we want to declare based on the graph that we have if something is a person, place, thing, or unknown. Those labels exist on some of our nodes, but not all of them. So let's go back into Cypher queries, method 1 queries. We're going to actually start getting into using the Graph Data Science Library, GDS. Now, in order to do that, starting at line 44, we're going to create some labels, or some properties here, not labels. We're going to create a property called PPTU person, and that's if I have my label is anywhere in this long list of things here. So I've just kind of manually gone through and created lists like place, administrative area, country, here's lake or body of water. These were the things that just made sense to me at the time as being a place. So if my node has any of those labels, I'm going to set PPTU place equals 1. Okay, so you can kind of see how I'm turning this into a multi-class classification problem. And lines 46 through 65. And I'm just going to paste them in sandbox and just give that a run. There's several commands in here. They're separated by semicolons. And when you do several commands, what you get is several different lines, and it'll show you the status of each of those commands. Okay, so that ran. That's cool. Okay, now if I'm going to create something called unknown here. This is when we don't know what our label is. Okay, so I'm copying lines 68 through 72 and dumping it into Cypher. You know, and I apologize that we're going like a mile a minute here. Basically, I'm covering a lot of information, and I'm hoping that you'll, on your own time, go back through and go through the nitty-gritty details of it. But I just kind of want to show you a whole bunch of stuff. Okay, so now we have PPTU unknown. Okay, let's skip over this one. Okay, now we're getting into the GDS library. The absolute starting point for all of working with GDS is creating these in-memory graphs. In-memory graphs, or graph projections they're sometimes called, are really efficient ways to store portions of your graph for doing calculations on. You cannot run anything in GDS until you've created an in-memory graph. Now, in general, we don't want to do what I'm about to do here, okay? But let me show you how to create this in-memory graph first. Okay, so this is going to be lines 78 through 88. Okay, so it's this function GDS graph create. And I have to give my graph a name. I'm going to call it all nodes. Okay, now this is why I say this is not a great idea. I have two dictionaries here. One of them is for the nodes and one of them is for the relationships. So for my nodes, I am going to say any node with a label of node. Okay, so that means every single node in my graph. Don't do that in general. We're just going to do it for demonstration purposes today. So that's taking every single node in my graph. And I am going to take some properties in. And the properties that I'm going to take, again, specified as dictionaries here, is a word vector embedding. Okay, I just happen to call it that. And it's that word vec property of the graph. Okay. If you're interested, I'm going to give you a link later on more detail on how to create in-memory graphs. It's a video series I've got going on. Okay, this second dictionary is my relationships. Again, I'm going to specify all relationships here. Not a great idea, but I'm going to specify that my graph is undirected. Now, we know we had a directed graph because I had nodes connecting through an arrow to other nodes, subjects connecting through a verb to objects. Okay. GDS, a lot of the GDS algorithms prefer to work on undirected. It's specified out in the docs which ones are which. But just for the sake of making this run smoothly, I'm going to call it undirected. So I'm going to run lines 78 through 88 here. Just going to copy and paste it over. And this is going to create our in-memory graph. Okay. So I can see here that I've got 657 nodes. Good. I have some more relationships than I expect. That's because what has happened here is that when you take a directed graph and turn it into an undirected graph, it basically makes two relationships. Okay, it makes the outgoing one and the inbound one. Okay, so that's just what happens when you create an indirected graph from a directed graph. All right, so now, you remember before we were talking about word tovec. Well, it turns out that there is a parallel for graphs called node tovec. Now let's think about that for a second. In word tovec, what happened was we scrolled through each word and we looked at their sequence within the sentence, and that's how we created our vectors. But there's no sequence in a graph. It's not like I go from this node to this node to this node, because I could also go from this node to this node to that node to that node. So a lot of times what these, we're trying to turn that graph, we're trying to turn each node into that graph, into a vector, an embedding. Okay, so what node tovec and FastRP and a lot of these things do is they do like random hops around the graph. Okay, so node tovec, we're just going to do that. Okay, so here's node tovec, and it's going to run. Remember, I called my in-memory graph all nodes, and it's going to create a 10-dimensional graph embedding. Okay, and I'm going to use this thing called stream. We're going to use write in a minute, but stream, all it does is it outputs the results to the screen. Okay, and it's going to return back this thing called node ID and embedding. Now, node ID is like this integer that doesn't really mean anything in physical space. It's how GDS stores its data on the nodes. So we want to return that as something that we recognize. So that's why you use this util function. We're going to return the name of that node as name, and we're going to return the embedding here. So let's just run 91 through 93 here and see what we get. Okay, give that a run. It's going to take it a second. Okay, there we go. Okay, so I have here a node and I have a 10-dimensional embedding. That's cool. And like I said, vectors are vectors. I can do any machine learning on a vector. It doesn't matter if it came from a graph or a word, right? It's just a vector. So we've now vectorized our graph, which is pretty nifty. Okay. Okay, now I used .stream just to output it to the screen, but I could also write those vectors to the nodes themselves. Okay, so we're going to do that. I'm going to write it to the nodes. I'm going to have a 10-dimensional embedding, and I'm going to call that thing N to V all nodes. Okay, so we're going to run lines 96 through 101. Okay, let's come back here. Okay. Give it a second. Okay, so it wrote to 657 nodes. That's cool. And you can go through, these are all kinds of hyperparameters associated with node tovec. Tuning these things is kind of an art. I have a blog post out there about doing it with a different embedding algorithm, but we've just gone with the defaults. Generally not a good idea to do, but we're just going with it for now. Okay. Let's now do some similarity calculations on graph embeddings. You can see here, instead of using cosine similarity on the word vectors, I'm going to use it on the graph vectors. Okay. So we're going to look at Barack Obama and Michelle Obama. How similar are they? Okay. Not that similar. There's like, 28% here. But again, this is a graph similarity, not a word vector similarity. So what we're really looking at when we do this is like how many nodes and relationships do they have, really how many nodes do they have in common? Okay, let's do it again for, let's actually just use the phonetic spelling here. Lines 112 to 114 between Barack Obama and Mitch McConnell. Okay, so I get a slightly lower similarity between those two than I did with word vectors. Okay, so it's just, something that, you can tinker around with. Let's go back to our notebook here. Okay, and we're going to create a data frame just of those, of the node vectors and the word vectors and some of the other columns here. Let me just run this so you can see what we've got. Okay, so I've got my name, my node labels, but then I have those four classes: person, place, thing, or unknown. I've got my word vectors. If I scroll over, I've got my node vectors. Okay, so let's compare. I'm going to just create some helper functions here for running some machine learning. I'm getting them all into scikit-learn format, basically, is what I'm doing. Okay, so here I'm creating my model. Now I'm going to do a 5-fold validation, k-folds of 5. I'm going to create my train test split with a test size of 25%. And then I'm just going to run super simple, support vector classifier. That's all I'm doing here, is creating a support vector classifier, and I'm going to return the accuracy. Okay, so this is just a function I created to do that. Let's run that now. So we're going to look at persons, people, and I'm going to run this for the word vector. Okay, so this is kind of like our baseline model here. Okay, and so here we go. Here's my confusion matrix, and you can see I got a mean accuracy of roughly 85%. Okay, check this out though. We have a pretty big class imbalance problem here. I got 119 people and 538 non-people. Okay, so the fact that we got 85% is actually not that bad. Now, let's do this. We're going to use the graph embeddings looking at people. Okay, I got 85% using my graph embeddings because, you know, relationships matter. I have posted a blog post showing this for a different graph, but showing how in some cases, if you were to compare word vectors to graph vectors, you can actually get a much higher accuracy using graph vectors. Consider that those word vectors were 300 dimensional and my graph vectors were only 10 dimensional. Okay, so I'm now storing less information on disk and I'm getting just as good of an accuracy. That is pretty nifty. I'm not going to run all of these. You can go through and run these yourself, but spoiler alert, it comes out, you know, roughly the same. So there's a whole bunch of things we could try here. We could tune hyperparameters for spacey word embeddings. We could tune the graph embeddings. We didn't tune the ML model at all. We just went with whatever scikit-learn wanted to do. Okay, so that's pretty cool. All right. Now, I mentioned before that we're going to actually do this with a second approach. Where do my slides go? Okay. Here, we're going to go now into method 2. Remember, I said we're going to actually do a Wikidata approach. Okay, so this is what I call the NLP Lite approach. Okay, NLP Lite, we're going to query Wikidata, and we're going to start by cleaning the text and getting the name entities, but then we're going to take those named entities into Wikidata. So for instance, on the right here, we've got the entry for Douglas Adams. We have these things called Q values and P values. So the Q value is a unique identifier for my subjects and my objects, or my nouns. That's going to be pretty handy, as you see here. And if you know Douglas Adams Q of 42, that's kind of cute. I also have properties associated with Douglas Adams. I have a description. Now my properties are called P values. And the P values are the verbs. So if I go and I get Q values and P values, then I have a really obvious graph going on here. So I could say Douglas Adams educated at St. John's College. Well, that's pretty straightforward. So the advantage here is the entity disambiguation. Okay, you will not find multiple Douglas Adams references, or you'll find a few, but there's not that many. So entity disambiguation is much easier with this approach. And then the drawback is that you're going to have to specify which verbs you're interested in, because there's a whole bunch of these P values that are associated with Q values. So that's the thing that is not so great here. Okay, so what we're going to do in this process, once we have the named entities, is we're going to obtain Wikidata items or claims for each entry and then assemble our graph. Okay. To do this, I have created a PyWiki bot. You need to create a token to do this to get those P and Q values. The slides show you how to do it. The notebook shows you how to do it. But ultimately, what we wind up with is we have our subject and our object. Each of those have a Q code, and each of those are labeled. I should have mentioned the labels. So let's see, labels are like descriptions. Okay, there is actually a specific P code that's associated with these labels. Okay, and then let's see, type is instance of, so like we would get Douglas Adams as an instance of human. Okay, so when we do that, this is the graph that we're going to get. We're actually going to go create this graph now. Okay, so to create this graph, let me just show you a few slides on this. Okay, GitHub, this guy, okay, slides. Okay, now let's go into slides number 3. These slides have a lot of information in them, so you can see exactly how I created these graphs. We're just going to start with the graph itself. Okay, so using Spatie, I'm going to get those named entities, and then I'm going to get the Q codes. Okay, I am going to specify my claims here. So my P codes, I'm going to specify. Those are my verbs. So I have to declare which verbs I'm interested in. Okay, and then I'm going to get all the targets, which are the objects for those verbs. I'm going to connect to Neo4j. Oh, P31. P31, each of these P codes and Q codes is associated with text. P31, that particular verb is called is instance of. Okay, so that's how we're going to actually get our node labels, is instance of. So like if you think about the Taylor Swift example, Taylor Swift is instance of thing and person. So let's see, and then we add all of our nodes and our relationships. Come here. Okay, so we get our Wikipedia summary for Barack Obama. We've seen that before. Okay, just visualizing it, we've seen that before in the slides. Okay, so let's look at some of our detected entities. Okay, this is interesting. My detected entities are a little cleaner because that phonetic spelling is gone because it didn't, Wikidata didn't actually recognize it. There's my pair programming coder. Her name is Bella. She is an adopted mutt. Okay, so I can see I've got some slightly cleaner subjects and objects here, which is kind of handy. Okay. We have some tags. We need to get rid of regex and words and things like that. So, you know, then you wind up with this code list. Okay. So I have some helper functions here that that are just how you would connect to Wikidata. You remember I had to get a bot token. Okay, that goes in here. I make my connection. And then here is actually how we would query with Wikibot. I have to get a query code here. That Q76 is Barack Obama. 42, like I said, is Douglas Adams. Okay, I really encourage you to go through the notebook that does this. That notebook, let's go into notebooks here for a sec in the repo. Okay, that is notebook number 3. Okay, so you could scroll through this notebook and get all the same information that I've got going in these slides. Okay, we start scraping Wikidata for our bot. So every named entity, let's actually look at this in the notebook itself. Okay, every named entity we're going to go and get P and Q values for. Let me scroll down here. First off, you can see that I'm missing a few of these entities. University of Chicago Law School, Republican nominee John McCain. This is a good example because what happened here with Spatie was it lumped all of these things together. If we had searched just for John McCain, we would have come up with a good entity. Okay, but in this case, we don't have that. You know, you can kind of get a feel for why that didn't happen. But ultimately, what I've done is with each of the named entities, I've obtained their Q values associated with each named entity. Okay, and we're going to use those here. We're going to have to dedupe that, obviously. But how we're going to get the verbs, okay, this is the real trick here, is I need to specify my P lists. So, like, I manually did this. Head of government is P6, country P17, place of birth. Okay, so I just went through and just grabbed these manually. That's the problem here. Remember, with Wikidata is I have to specify that manually. Okay, and I run this. This takes a while to run, which is why we're not doing this live. You can see that one took 9 minutes. But I am going to wind up with a graph where I start with a data frame. I have a source, I have a target, I have a source Q value, I have a target Q value, I've got relationship name. You can guess where that's going because you can guess I'm about to ask you that question. Okay, now here's how we use the official Python driver in this notebook. Okay, and this official driver, here's just a class for making that connection. Again, we're going to do it the same way that we did before. I have to have the URI for my sandbox instance. I need a password. Okay, and I'm just going to populate the graph here. You can go through some blog posts that I have if you want to get into the nitty-gritty of how to create the graph. But basically, it's these functions that are down here for how to create it. Okay, so now what we're going to do, we're going to spin up another sandbox instance. And we're going to spin up a super special one. And where we're going to get this from, if you go into the README, okay, what I want you to do, we're going to go to the repository README now. Okay, so that's what's down here. And see this quick links for the workshop? Okay, we already have a running Neo4j sandbox. Now the way sandbox works is I can't have multiple of the same types running at the same time. But I've got this special one here, which actually isn't in our list. This is special for you guys who are attending today. We're going to click on this Neo4j blank graph data science sandbox. Okay. And it's going to create us a new blank sandbox graph data science instance. So let's click create there. These take a little longer to create than just a normal blank sandbox. They have a bit more memory and they have a bit longer timeout. So we've created it here. Probably if I click open, I'm going to get like some sort of 404. Oh, that's nice. It's firing right up. Cool. Okay, while we're waiting for that to happen, remember notebook number 3 is going to have how, it's going to have the nitty gritty on how I created that graph, but we're just going to pre-populate it for the sake of today. And that's going to happen again. Oops, I got out of my repo. That's no good. GitHub.com. Okay. Let's go back into our repo here. Okay, so where was I? We're going to go into Cypher queries, starting queries, and we're just going to pre-populate this repo. I have the query here for you using a JSON file. Okay, so we're going to grab line 25 in that starting queries section. Okay, so let's go. Here is our new browser window. Okay, and I'm just going to copy and paste that in, and this is going to take a second again as we go and we manually grab all of that. Okay. All right, cool. Now we have 1,325 nodes and 1,638 relationships, and you can see there's a whole bunch of relationships in here. Okay, cool. So now we're going to make this graph a little bit more interesting. So we're going to go back into our repo. Okay. We're going to go back into the Cypher queries directory and we're going to do method 2 queries. Okay. So let's go to the top here. We have some duplicates. We're going to get rid of them. There aren't many. So that's going to be lines 10 through 13. Okay, so I want to make sure we're doing this in the correct graph here. Okay, let's see what we have here. We just got rid of 6 of them, so that's not a big deal. Okay, now we're going to convert our string labels to a list. This is just a quirky thing about how the Python is working. we have a list of strings that we need to get out here. So we're just going to run these really quick. It's just getting into the format that Neo4j likes. I'm not going to spend a lot of time on that. Now, we're going to update our node labels just like we did before. So instead of having type node, now I'm going to add all different types of labels that these guys might have with them. Okay, and give that a second. All right, now I have a graph. Okay, let's zoom out here. Okay, I have a bunch of different node types. I'm zooming way out. Okay, but this is our graph. That's what it looks like. So that's cool. I've got humans and I've got states of the United States and universities, and we actually can't see the whole graph here because these browser windows are limited to 300 nodes, but it's there. We have a graph. Okay. Now, where was Barack Obama born? Okay, why don't you take a second, because it's going to be a lot more straightforward here. Why don't you take a second and see if you can figure that one out on your own. Throw in chat what you think it might be. I'll give you a hint in a minute. All right, what do y'all think? I am going to give you a hint that I'm going to throw into chat. Oops. If I can copy and paste things correctly. Here is a relationship that might help you. Okay, so let's take a peek here. Okay, so what I'm saying here is that I have a node named Barack Obama. That node is pointing at some place of type node, but the relationship type is place of birth, and we're just going to return the names of those places. Okay, check it out. I've got the name of what is presumably a hospital. I've got Honolulu. And then I've got Kenya. Okay, this is following, different news things where people were claiming that Barack Obama was born in Kenya, not actually the United States, but it is part of the Wikipedia page. So, we kind of got to go with it. All right, cool. We are in the home stretch here. Let's talk about what we're going to do. Okay, let's go back. We are going to create a new label. We're going to just do place versus not place in this one. Okay, and so if you start at line 27, we're in method 2 queries, Cypher. Okay, we're going to match any node where the type is in one of these types. Now I manually picked these. Again, subject matter experts are important. Okay, so I created a list of things that I thought would be places, and I am going to set a property called isPlace equals to 1. Okay, so we're going to copy lines 27 through 62 now. Okay, I'm going to just dump that into our sandbox. Okay, so I have 413 places, or 413 nodes got this property set to them, right? Okay, now we're going to set everything else is place is 0, so it's not a place. Okay, so that's 906 properties. Okay, cool. Now, we now have to create our in-memory graph because we are going to do our machine learning now. Okay, so I am going to create a graph. Again, I'm calling it all nodes. Remember I said not a great idea to create a graph of your entire thing, but this is just a slightly different format. I'm saying everything that has node type of node, which is basically our whole graph. Here is a dictionary for our relationships. Again, I'm saying all relationships, not great. I also say orientation is undirected. Okay, remember that's because a lot of GDS algorithms like undirected graphs. Not all of them, but a lot of them. So we're going to copy lines 74 to 83. Okay, let's give that a copy. Okay, remember it doubles my relationships because it takes a directed relationship and then makes it go the other way as well. Okay, so where are we at now? Okay. Now, like before, we are going to create a node tovec embedding. Okay, I'm going to create a 10-dimensional embedding again. And I'm just going to skip over that part where we show it up, stream it to the screen. I'm just going to write it to the nodes. Okay, so let's give that a run. Okay, cool. Now we're going to run lines 94 to 97. Fast RP is just a different way of creating an embedding. It's basically, again, skipping around the graph. I've written a blog post about that one, but you can read up on it. Again, I'm just using a 10-dimensional vector. Okay, let's give that a run. I have not done any tuning of these embeddings. The only thing I've done is told it how many dimensions it needs to be. We like fast RP because, well, it's fast, like, the name suggests. Okay, so now I have embeddings. Okay, I've got nodes, I've got embeddings. Now we can do some machine learning. I don't have any word vectors in this case, that's okay. We are going to now run Notebook 4. Remember, Notebook 3 was how we populated the graph. Notebook 4 is how we're going to do fun stuff with it. So let's give that an open. Okay. Like I said, we're using the official Python driver. So we have to install it. Okay. It's going to just take it 1 second here. Thank you, Tomasz, for posting the link to that blog post. Why don't you also post yours on NodeDevec? How NodeDevec works. Okay, so I'm just going to bring in our usual data science packages here. I've got my class that I used to create my connection. We talked briefly about that before. Okay, now I need to make my connection to our sandbox instance. So I'm going to remind you how to do that. Remember, we're using the blank graph data science instance. So let's drop that down here. I'm going to use connection details. Okay, so I clicked on this drop down and then on connection details. Okay, I'm going to copy my URL and then I'm going to paste it into my notebook. Okay, and then I'm going to go back and I'm going to get that password, that 3-word thing. Okay, I'm going to paste it in here. Okay, now just really quick, here's where I'm going to make the connection. Think of this kind of like how you'd use SQL Alchemy. You've got like cursor functions and whatnot. But I can run a query. I can run a Cypher query right from Python, which is cool. You can do that in PyNeo as well. I'm just going to show you how it's done here. And I get my count back of nodes. I like to do that just to make sure that I've actually properly connected and I've gotten all of my data into Python. Okay, so let's just look at our embeddings. Remember, I created embeddings in the browser. I'm going to just drop those down via TSNE, T-distributed stochastic network, TSNE. Basically, I'm doing a dimensionality reduction of my 10-dimensional vectors into 2-dimensional vectors. Okay, and I am now going to create my TSNE plot. Now, in a perfect world, I'm saying I want 2-dimensional, and you remember I have place versus non-place. Okay, in a perfect world, what I'm going to get is a graph where I've got a nice little dense cluster of place, and I have a nice little dense cluster of non-place, and they're separated by a nice distance. And, the universe is not kind to us. We don't exactly get that. I've got a nice little blue cluster over here. What is blue? Blue is place, that's my 1, and red is non-place. So unfortunately, I don't get that nice clustering in this two-dimensional space. That was for node tovec. Let's look at it for FastRP. And this is just using scikit-learn. Scikit-learn, for those of you who are students or are not data scientists but working with them, this is just a really common open source Python package that has a lot of machine learning capabilities built into it. And, again, this is really nothing to write home about, okay, but it is what it is. Okay, so now let's do some actual machine learning. Okay, it's going to be the same process as before, fivefold. It's going to be, we're going to have a class, and it's coming. Support vector classifier right here. We're going to fit it. We're going to get our accuracy. Okay, let's look at what our starting dictionary is going to look like. Here, by the way, this line, this model DF, this is how you, this line right here is how you create a data frame using the official Python driver. So you can see here I've got a name, I've got a type. My category is place versus non-place. So we're basically just doing binary classification this time. I want to predict 0 or 1 based on my different embeddings. So let's give that a run. Okay. Okay, so this was using node tovec. And I get, roughly 73%. Anything better than 50% means I'm doing better than a chimp flipping a coin. Okay, so the accuracy isn't great. It's not bad. Remember, I'm only using a 10-dimensional vector, and it is not at all tuned. Okay, you can see my class imbalance here. Okay, let's do this with FastRP. Okay, so FastRP, I got 71%, not great, but there's a few things that we didn't do here. We did not optimize the embeddings at all. We these graphs that we're dealing with are really small. When we're talking about graphs that are on the 1,000 node level, that's a really small graph. People who start getting into like the enterprise edition stuff, you're talking about millions of nodes. Okay, obviously the computational complexity is greater. You're dealing with larger machines, big AWS instances to do those calculations. So adding more data is always a good idea if you can. So we also, like I said, didn't optimize any of the embeddings. You could try GraphSage, which is a different embedding model. You could try bringing in node properties into your graph. So it turns out that like FastRP has a thing called FastRP Extended, where not only does it consider random hops around the graph, but it considers the properties that are attributed to each node. So that could get you some better accuracy as well. Okay, we have a grand total of like 4 minutes here, so we need to wrap up. Okay, if you go through the slides, I have descriptions on all of these things that we've talked about. These are all available in the repository, and the video will be made available by Neo4j shortly. So let's get back into our slides. I just want to remind you, we had those 2 key concepts at the very start of this workshop. And those are the 2 things that if you took away nothing else from today that I want you to remember. The first is there is no proverbial quote-unquote silver bullet associated with NLP. We've talked a lot. NLP is messy. The signals are noisy. You need to have subject matter experts involved. Okay. The subject matter experts can help you, like in that case where we found that Michelle Obama was not in the graph. All right. The next one, the quality of what you get out of the graph depends on the quality of what you put into it. Okay. So that's the case where we've got like 2, we don't have a lot of nodes. Our relationship labels aren't great, particularly in that method 1 approach. So, it takes time to really properly develop this. Also, let's see, we did not do a lot of any tuning of any, word vectors or anything like that. And we only used a very basic model. We used Spacy. Spacy is a great, easy to use NLP tool, but there are better ones out there, more sophisticated ones like BERT and BERT's variants. So consider, what your NLP model actually is. We've already talked about adding data to the graph. We've talked about word vectors and, how you could put word vectors in as your properties. I actually put those in the graph for you to try later. Remember in that method 1, I had that 300 dimensional word vector. You could use something like FastRP extended to add those into your FastRP and your random hops and see how that might benefit you. And then we also talked about GraphSage. We mentioned it briefly. It's a very sophisticated embedding algorithm beyond the scope of today. People always, always, always ask, can I use neural networks? Absolutely. Absolutely. There's graph neural networks out there. TensorFlow just released one. There's also JRAF and all of these different things that can do graph embeddings for you. But the thing I will tell you is it's always more efficient. Let Neo4j do as much as you can before you suck that data down. Because Neo4j has built-in embeddings, I recommend you try those first. That being said, you're just winding up with vectors. So as long as I can convert my vector to a tensor, I could use TensorFlow and Keras, I could use PyTorch, any of them. Okay. Phew, problems that we could solve. We talked about some of these, but community and cluster detection, very easily done within GDS. Node classification and link prediction. We kind of did node classification today. Link prediction is a whole new thing. What's the probability that this node should be connected to that node? Beyond the scope of a 2-hour workshop, absolutely doable. Graph to graph classification, super sophisticated. Is this little graph over here like this little graph over here? Unstructured text and NLP question answering systems. We talked a lot about that. Whew, and we've come to the end of our time. Again, I just want to say thank you for attending. Please reach out to me like on Twitter if you have questions. That's my Twitter handle on the bottom. The top link is where to find me on Medium. I've got a whole bunch of graph blog posts on there, including how FastRP works, like the math behind it, how to tune FastRP. You might see more tuning blog posts coming out on other embedding algorithms. The middle link there, I have a video series. I put out a video every week, and it's called Bite-Sized Neo4j for Data Scientists. Each week, I try to take one small subject and try to cover it in 5 minutes or less. Not always successful on that 5-minute thing, but if you go to that web page, all of my videos are there. We're up to 16 parts now, and my goal is to add a new part every week. So with that, thank you again. I'm going to turn it back over to Alex. Thank you, Alex, for helping. Thank you to Tomaj for helping answer questions. And that's it.
Super. Thank you very much, Claire. Amazing. Thank you, Thomas, also for jumping in with the questions and the chat. Yeah, I don't think I have much to add. It was great overview. Thank you for presenting and showing us the overview and the hands-on part of it with all the all the live execution and the NLP. So it was really good. I think people enjoyed it. I see lots of claps for you, Claire. So I think that's great. It was a very
Thank you guys.
Fun and interactive session. Yeah, I can only repeat what you already said. So we will share the video, we will share the slides, so you can take your time. If this was maybe in the end a little bit too quick, you can take the slides and the video and do it in your own pace. We have a next session coming up next week. If you're interested in Bloom and more data visualization, if that is something you are interested in, there is a session coming up in a week's time. If you want to reach out to us, to Claire, to anybody, tweet us at Neo4j or find us on our Discord community forum, where we have also great chats and conversations going all the time. So you're welcome to join us there. Yeah, and with that, I wish you all a great evening. Thank you for joining. Thank you for making this fun for all of us, and see you soon.
Thanks, everybody.
Ciao. Bye.
Bye.